Okay, this is section 2.6 and least squares. Now we aren't really ready for the theory of least squares yet, in that we just don't quite have the machinery. So I guess this is least squares solutions of equations. And this boils down to the idea of, I want to solve AX equals B, where A is M by N and M is greater than N. So if I want to solve that, what happens here is I have too many equations for the number of unknowns, right? So take something like similar to the example they start off with. So I have three equations, x equals 1, y equals 2, and I'm going to go with x plus y equals 4. They went with 3.001. But if you look at this, it's pretty obvious this is inconsistent, right? Because x is 1, y is 2. There's no way that x plus y is 4. And so if you look at this from a matrix perspective, though, this is A times the vector x equals b, where, right, A is 1, 0, 0, 1, 1, 1, so it's 3 by 2. Our vector x is given by the variables x, y. Oops. And our vector b is given by the vector 1, 2, 4. And so generally speaking, what we know, right, if I have more equations than unknowns for these linear things, probably it's going to be inconsistent. If this 4 was a 3, well, no, that would work. But generally, it's going to be inconsistent. And so what do we do? And again, to me, this is a lot of trickery at this point in this solution, because we don't really see why it should work. But if we solve A transpose AX equals A transpose B, instead, we get X if A transpose A is non-singular. Okay, that shouldn't be a surprise, right? If I do A transpose X, then I get a square matrix for 1, and it happens to be symmetric as well, but I get a square matrix, and so I should have a chance of solving this new equation and new matrix equation. And certainly I will have a solution if A transpose A has an inverse. Okay, so this is great. And it turns out that typically for data purposes, okay, when you're working with data, A transpose A is non-singular. Okay, and I can't really put it in other terms real well, because we just aren't there yet. But typically it will be non-singular. And then this x that we find, call it maybe x star, this x star that we find minimizes the 2 norm of ax minus b. Okay, so what we would like is we would like that to be 0. It's not going to be. But what we find is if we do our 2 norm of that resulting vector, so we take ax star minus b, 2 norm, that's less than or equal to any other possible x. Okay, so it's the smallest deviation from b, you know, this ax here, minus b. It's the difference between ax and b. Okay, and we're going to have a difference if we can't find an exact solution, but it minimizes that. So this is the minimizer of this 2 norm for all x. So that's, you know, that's why it's called least squares solution. Now the square, well, remember a 2 norm involves squares, okay, from our project. So that's why it's called least squares. And it is that simple, really. So let's go back to our original problem here with the, you know, x, y, and x plus y, and our 1, 0, 0, 1, 1, 1 type thing. Okay, so I want to solve 1, 0, 0, 1, 1, 1 times x, y equals 1, 2, 4. Okay, I'm going to multiply both sides by this transpose, so that's 1, 0, 1, 0, 1, 1 times 1, 0, 0, 1, 1, 1 times xy equals, and remember the transpose on this side, 1, 0, 1, 0, 1, 1 times 1, 2, 4. Okay, on the left-hand side, 1, 0, 1 dotted with itself, I get 2. And 1, 0, 1 dotted with 0, 1, 1, I get 1. Now, we should see this is symmetric, and I get 1 there, and then a 2 there. So now I wasn't assuming that I get both 2's down the diagonal, but if you look at this generally, right, it is symmetric. And then on this side, 1, 0, 1 times this thing, I get 5, and 0, 1, 1, I get 6. And so that's what I want to solve. Well, I'll set up my augmented matrix, right? And maybe I'll just swap rows to begin with. And so that goes to 1, 2, 6 and 2, 1, 5 like that. Then the next thing I do is I'll take row 2 minus 2 row 1 and put that back into row 2. And so I get 1, 2, 6, 0, minus 4 and 1 is negative 3, and minus 12 and 5 is negative 7. And so now I'll do negative 1/3 times row 2. 1, 2, 6, 0, 1, 7/3. And then finally, row 1 minus 2 row 2, and put that back into row 1. So I get 1 and 0. And negative 2 times 7/3 is negative 14/3. 6 is 18/3. And so that's 4/3. And 0, 1. And 7/3. And so that says my best x star to solve this is 4/3 and 7/3. Now it's not exact, right? Because if I take a times x star, that is my 1, 0, 0, 1, 1, 1 times 4/3 and 7/3. And I get the vector 4/3, 7/3, and 11/3. And now if I take ax star minus b, I get 4/3, 7/3, and 11/3. And that's minus 1, 2, 4. I get the vector 1/3, 1/3, and negative 1/3. Okay, and that's as close as I'm going to get in the 2 norm. And so the 2 norm of this minus b is equal to the square root of 1/3 squared plus 1/3 squared plus minus 1/3 squared. And so I get 1/9, 1/9, 1/9. That's 3/9. So the square root of that is the square root of 3 over 3. And so that's as close an answer as I can get in that 2 norm. And so that's all least squares is. And so, for instance, suppose I have the data, x and y, and x is 1, 2, possibly even a 2 and a 3, something like that, and then y is maybe like 2, 3, 4, and 4, something along those lines. Then to set this problem up, what I want to do is, I've got my data here, and it looks something like this. There's x, there's y. I'd like to find the best fitting straight line, so that's y equal mx plus b. And so I just set that up. We've set that kind of thing up already. We did something like that on a quiz, right? I can set this up as each of the data points. So I have m times 1 plus b needs to be equal to 2. M times 2 plus b needs to be equal to 3. M times 2 plus b needs to be equal to 4. And m times 3 plus b needs to be equal to 4. And so you see this problem just becomes the matrix problem of 1, 2, 2, 3, 1, 1, 1, 1 times mb is equal to 2, 3, 4, 4. And so if I multiply through by the transpose, 1, 2, 2, 3, 1, 1, 1, 1 times 1, 2, 2, 3, 1, 1, 1, 1 times MB is equal to 1, 2, 2, 3, 1, 1, 1, 1 times 2, 3, 4, 4. I now get a 2 by 2 problem. So I'll get the sum of these squares here, the x's. So I get 1 and 4 and 4 and 9. So that was, I think, 9 plus 9. I get 18. And then on the diagonals, I'll get the sum of that first row. So I get 3, 6, 8, and 8. And then the bottom, I get the number of data points, 4. And that's M times B. And here I get 1, 2, 2, 3 times, or dotted with this thing, and so that's 2, and 6 is 8, and 8 more is 16, plus 12 is 28, I think. And then the sum of these, 2, 5, 9, 13. And so there is the least squares problem I need to set up. I'm not going to solve it. But we could get our M and B, our best fitting M and B that way. Okay, at least in the sense of minimizing that 2 norm. And so, you know, we can do that. But the least squares still works. You know, I could, instead of trying to fit instead of trying to fit a straight line to that, I could try to fit a quadratic or something like that. You know, so if I had y equals ax squared plus bx plus c, you know, that kind of thing, you know, then I would just make my data that way, right? I'd have a times 1 squared plus b times 1 plus c needs to be equal to 2. And a times 2 squared plus b times 2 plus c needs to be equal to 3. A times 2 squared plus b times 2 plus c needs to be equal to 4. And a times 3 squared plus b times 3 plus c needs to be equal to 4. And so then I would set up, again, matrix problem, 1, 1, 1, 4, 2, 1, 4, 2, 1, and 9, 3, 1, all times my A, B, C, and want to get, was it 2, 3, 4, 4. And so I would, again, I'd multiply by the transpose of this matrix on both sides. I would get a 3 by 3 system, hopefully be able to solve that, and get my best fitting quadratic. Okay, so that is this idea of least squares and section 2.6. I think that was everything in it. I'm taking a last look. Yeah. So I think that's what they had in it, and so we'll call that good for chapter 2.